Hello guys, in this video we're going to try to solve a LeetCode medium problem titled Subarray product less than k. So in this problem we're given an array of integers, nums and an integer k, and we're expected to return a number of contiguous subarrays, that's subarrays that are next to each other. So a subarray could contain one or more elements. And the constraint there is that the product of the elements in the subarray is strictly less than k. So it's not equal to or greater, it is less than k. And we can see here that the valid subarray is here, and this is invalid because it is 100, which is not strictly less than k, which is 100. So we're going to attempt to solve this using the sliding window approach. And usually when you see a problem that has like a constraint metric, for example, in this case, the constraint metric is that we're looking for the product of all elements, and then there's a numeric restriction on that metric, which in this case is that it should be strictly less than k, and this is what makes it valid. So that seems to suggest that sliding window would be a good approach. So that's just like a general overview on how to know whether a sliding window will be suitable or something for a problem. So yeah, like I said, if there's like a constraint metric and there's a numeric restriction on that metric, and we're asked to find valid subarrays in some way, so that is usually a good candidate for using the sliding window approach. And the sliding window approach in this case usually involves two pointers. That's a left and a right pointer. So usually the left and right pointer would start from the first index, which is 0, and then we would advance, or we would add elements to the right of the current index, the left index. We'll advance r, which is the right pointer, so that we'll add elements, and if at any time the window is invalid, then we would remove from the left. So removing from the left means now advancing the left pointer, which automatically discards the elements in the left. So hopefully this will make more sense as we proceed to solve the problem. But let's see how it would work here. So in this case, 10 is valid because it's less than 100. And then we advance the right pointer to here. So now r is here. I'll cancel it from here. So 10 times 5 is 50, which is less than 100, so that's valid. And then we advance right to here. So 10 times 5 times 2 is now 100, which is not strictly less than 100. So now our subarray is invalid. So we now advance L. So L will now come to here. So 5 and 2 is valid. 5, because 5 times 2 is 10. So we advance R. And now we have another valid window, 5 times 2 times 6, which is 60. And now we've run out of elements. So now the question is how at any given point where we have a valid window, how do we get the number of subarrays? So in this case, 5 to 6, we see that we have the number of subarrays here would be 5 to 6, 5, 2, and 6. Oh, sorry, let me say that again. So left, right, we actually see there's a formula here which can help us to find the number of valid windows. So 5 to 6 is 1. 5 to 6 here, 1, 2, 6, 2, and then 6. So left, right, if there is left plus 1 and right, so that's another sub array, which is valid, and then we keep doing that up until we get the very last element. So in this case, it will be 3. So using that same approach in this valid window 10, 5, we see 10 and 5 is one valid subarray and 5 is another. So in this case, it will be 2. So following this formula now, the number of valid subarrays at a given time is given by right minus left plus 1. This is actually a general way of finding the number of valid elements in a subarray, and in this case, the number of valid contiguous subarrays in a given window. So here we do have, in this case, we know that the answer is 2. So let's try this approach. Right is 1, left is 0. So 1 minus 0 is 1 plus 1, 2. In this window, we know the answer is 3. Let's try this formula. So right is 0, 1, 2, 3. So 3 minus 1, which is 2, then plus 1, which is 3. That gives us 3. So using this now, we're going to attempt to then solve the problem. And the algorithm is that, like I mentioned earlier, we advance to the right, we add elements to the right, and then we remove from the left whenever the subarray becomes invalid. So at each moment, we are only considering valid subarrays. So let's start by declaring so we have a left pointer, right pointer, which will start from 0. We also want to have the current product. So I'll actually name this current product, which will, because we are dealing with products, we want to initialize that to 1, because if we have 0 and you multiply that by any number, we would always get 0. And then we want the answer. This answer, we initialize it to 0, and we'll add the numbers to it as we encounter a valid subarray. So now we're going to now traverse through the nums array. So for actually, I would use right to traverse through this array for r in range. So len of nums. So meaning that I can take it away from here and I can actually replace that with answer. So for right in range of len of nums, so we want to current product times equal to, so the current product, we want to add or multiply it by the current element and the nums array. So the current element in nums array is given by nums right. So let's say we are here, we're in 10 and we just multiplied 5, right? We've moved to 5 and we've added it to 10, so that's 50. But we need to do a check before we do anything else that it's less than, that our current product is less than k, which is the construct we have. So while the current product is greater or equal to k, remember that we're dealing with strictly less. We want it to be strictly less, so we check it's invalid if it's greater or equal to k. Then what we do is what? We remove from the left. And how do we remove from the left? We divide the element on the left. We divide by the element on the left, so which is given by nums left. So what we've done here now, let's assume we've moved to 550, so it's valid. So that means this while loop will not run, and the rest of the program would continue. So if we move to 2, we'll now see that it's invalid. So this current product will divide by the element at the left, which is 10. So given that we divided by 10, we want to advance L to the next element. So we do left plus equal to 1. And then, yeah, it moves to that. And then the algorithm continues. So when by this time, we must have a valid sub window or sub array. So our window is valid. So what we now do is we add to our answer, and our answer is given by using the formula that we have, which is right minus left plus 1. And at the end of the day, we return answer. So let's see if this works. Index is out of range. Why do we have index out of range? Let's see. Index is out of range. Okay. So let's current product times equal to nums right, while current product less than equal to k, current product less than equal to nums left. Okay. Yeah, so in a situation whereby k is 1, for example, if k is 1, then we, or 0, because let me see the test case that failed. So yeah, if k is 1 or 0, then this will be out of bound, because yeah, left will just keep on going. The current product is 1, and whatever you times by 1, as long as it's positive, it will always be greater or equal to 1. So we should have a special case whereby if k is less than or equal to 1, that means our answer should be 0, because there's it can't get strictly less than that. So we should have, if k is less than or equal to 1, then return 0. Now let's try running that. Yep, so that's been accepted. Let's submit, see whether, and yep, that worked. So yeah, the time complexity is O of n, basically due to this for loop here. Now one might ask, okay, but we also have a while loop here, but this is actually an amortized O of 1, because if this while loop can only iterate n times in total for this entire algorithm. It can only do n times in total. That's the maximum it can do. And if it ever reaches that maximum, that means it wouldn't run at all for other times or other iterations of the for loop. So it's like what we call an amortized analysis. So once you keep removing from the left and keep going, if it eventually gets to the end of the last index in this array, we cannot proceed with this for loop because we've run out of elements. So throughout the life cycle of this program, this would run maximum of n times. So if you average it out, it's equals to O of 1 amortized. So that's why we don't consider this as a worst case of O of n. So amortized is, the solution is O of n, time complexity, and then space complexity is just O of 1. It's just constant because we're just using variables here. And yeah, that's it. Thank you.